So this cycle is based on the Ericsson cycle. So usually I'll be looking at problem solvings for all these Stirling, Ericsson, Atkinson dual combustion cycles. Okay, so I will show you all the problem solvings. Until you are familiar, how are you going to solve any problem of any different category? Okay, how to solve cycles of different category. So that is why I go into more examples so that you will be able to figure out how to calculate heat supply, where to look for the heat supply, where to look for the heat rejected, where to look for the network out, how to calculate the thermal efficiency, how to calculate the gross work ratio, mean effective pressure, and Carnot efficiency, and so on and so on. Okay. So at the beginning of the isothermal compression of an ideal Ericsson cycle, using A, the pressure, volume, temperature are 100 kPa, 0.08 meter cube, temperature 20. The volume ratio of the isothermal compression is 5:1, and after isothermal compression, the volume of the air is doubled during the constant pressure process. So first of all, you have to know what's Ericsson cycle. So you can see based on these two diagrams, you can see constant pressure and constant pressure. Okay, these 2 to 3 and 4 to 1 both are constant pressure. Okay, and then 1 to 2, okay, 1 to 2 is isothermal, 3 to 4 is isothermal. So in this cycle, there are no isentropic process. Because here, Ericsson cycle, there are no isentropic process. Okay, where you have two constant temperature, two reversible constant temperature processes, and two constant reversible constant pressure processes. It's still in clockwise direction. Okay, so that's Ericsson cycle. So based on the question, here are the given data: pressure, volume, temperature. First thing, find out the mass by applying ideal gas law. Okay, so that is the mass. PV equals to MRT, pressure 0.1, volume 0.1, temperature 0.1. Mass and the specific gas constant, they are constants. Okay, so you can find out the mass of 0.0951 kg. Then the next thing is, now, is stated in the question, the isothermal compression. You can see here, isothermal compression. Where is the isothermal compression? So you can see on TS, the isothermal is 1, 2, and 3, 4. So 1, 2, and 3, 4. So 1, 2, you can see now very clearly on the PV diagram, 1 to 2 is compression, 3 to 4 is expansion. Okay, so these are the things that you have to take note. Okay, so the first thing is you must know how to draw the PV and TS, and based on that, you must be able to analyze. Okay, so they say the volume ratio of the isothermal compression. So this is your isothermal compression process. 0.1 is greater, V1 is greater than V2. So that is why you take V1 over V2 equals to 5. Okay, V1 over V2 equals to 5. So we know V1, so we can find V2. So this value can be found. Then the next thing is, okay, so we use PV equals to MRT. Okay, the pressure unknown. Okay, the volume we have found, the mass, the R, and the temperature. So the temperature is 293 and 293 because T1 equals to T2. So 293 temperature. So from here, you can find out your pressure 5 bar. Why they times it with 10 power 2? Because they're converting it into kilo. Okay, K. Because your R is K also, kilo. So now we have got this, this first row and second row. Then when it goes to the third row, we know that pressure are the same, 0.2 and 0.3. So both the pressure is 5 bar. So in the question, they have said, okay, V3 over V2 equals to 2. Okay, so during the constant pressure process, okay, heat addition process, the volume is double. So V3 equals to 2V2 here, given in the question. So you have to read the question carefully, yeah, to find out your V3, which is 0.032. So once you know pressure, volume, you can find out pressure. Okay, so temperature are the same between 3 and 4. Temperature 3 and 4 are the same. So that is why it's 586 here. Pressure also you have already got the pressure of 0.1 and 4. 0.1 and 0.4 are the same. See here. So you've got the pressure and you have got the temperature. So use ideal gas law to find this volume here. Okay. So it's 0.16 million. Okay, so the heat supply and heat rejected. So heat supply, where is heat supply? So look at TS diagram. That is 2 to 3 and 3 to 4. 2 to 3 is what process? Is constant pressure. 3 to 4 is isothermal. So the change of entropy, why do we come to change of entropy this time? Because isothermal. Because isothermal, if you want to find heat supply or heat rejected, you have to take the temperature multiplied by the change of entropy. From the previous explanation, actually we have got this formula. Okay, so you use the change of entropy to find the heat during isothermal process. One is heat supply or heat rejected. So you can make use of 3, 4, the formula to find the change of entropy of 3, 4, and 1, 2. So 3, 4 is heat supply. So remember, for isothermal, the heat is T times change of entropy. So that is why you find out the change of entropy here. Okay, so the heat supply would be found as 25.75 for these 3 to 4. Okay, then heat rejected, they consider here. That means they consider during isothermal. Yeah. So the change of entropy is here. Okay, so that is S1 minus S2, which you can take as the same because they are using the same pressure ratio. Okay, same pressure ratio. Okay, so you can find out the heat supply from one. This should be heat rejected, not heat supply. Heat rejected, heat rejected, heat rejected. Then you can take out network out is equal to heat supply minus heat rejected. Okay, so based on Ericsson, they take here as heat supply and there as heat rejected. Okay, then the network, then the thermal efficiency. Thank you. Stay safe.